Hello everyone and welcome to our WJE webinar. My name is Jon Lewis, the manager of WJE's Chicago office, and I'll be your moderator today. Thank you very much for joining us. Our topic for this webinar is facade access equipment. Is your building OSHA compliant? The Occupational Safety and Health Administration requires that building owners provide assurances to users of facade equipment such as window washers that the equipment meets all applicable OSHA requirements, one component of which is meeting the minimum capacity requirements to be able to safely support workers and work platforms or scaffolds. During the next hour, we'll share additional insight into these OSHA requirements and how you can ensure that the workers on your buildings have structurally adequate anchorages for exterior facade work. WJE facade access experts and structural engineers Richard Dethlefs from WJE Saddle Office and Gwenyth Searer from WJE San Francisco office will explain OSHA's requirements in lay terms and discuss methods available to verify structural compliance. Finally, we hope to be able to answer your questions about all things related to facade access. So to begin, we'll go over kind of the learning objectives that we have for today, which will also double as an outline. We'll start with kind of a primer about common types of facade access equipment, including some photos so you can relate that to some equipment that you may or may not have on buildings that you're familiar with. In lay terms, we'll go over some of the basic design requirements that apply to this equipment. We'll also focus on responsibilities that building owners and property managers have regarding facade access equipment. We'll cover some of the aspects of testing and inspections and things that you have to do on kind of a continual basis with respect to this equipment. And we'll close by covering some core industry practices that you should be aware of, specifically as it pertains to load testing. To start, let's review some of the types of facade access equipment and the activities that they're commonly used to perform. I should say we'll not give an exhaustive treatment of every possible arrangement that can be used to access the building's facade, but rather focus on some of the more common equipment used on high-rise buildings in the United States. So facade access. What do we need to get access to our building facades for? Probably the most common usage of facade access equipment is for window cleaning. Most buildings will have their windows cleaned several times a year depending on the climate. Facade access is also required for general facade maintenance, which may include sealant repairs or window reglazing, for example. Occasionally, more in-depth repairs are required, such as painting, masonry replacement, or metal repairs. These activities are all deemed construction activities by OSHA, and there are different requirements for activities deemed as maintenance versus those deemed as construction. Further, the definition of construction is not well defined in OSHA, but generally speaking, anything beyond minimal maintenance qualifies as construction and triggers additional, and in some cases, more stringent requirements. Let's now briefly review some of the common types of equipment. The photo here shows a powered platform installation, which is sometimes referred to as a building maintenance unit, or BMU. It has a roof car or carriage that traverses the roof perimeter, in this case on a track, and raises or lowers a working platform which provides access to the work area on the facade. The platform for BMUs is commonly suspended by two independent sets of cables, and thus the workers are permitted to attach their personal fall protection directly to the platform. This platform has specialized shoes or brackets that engage the facade to provide continuous protection against wind sway. For simplicity, we'll not focus on the specific mechanical or electrical requirements for the roof carriage, since they are many, but rather focus mainly on the structural requirements for facade access equipment more commonly found on buildings in the United States. Another type of powered platform is this modular system, commonly referred to as a swing stage. In this case, the platform and the hoists are furnished by the contractor to access the building on a temporary basis. These systems are usually only supported by a single cable at each end of the platform, and thus the workers are required to have their personal fall protection equipment secured to independent lifelines, which are in turn attached to structurally sound anchorage points located on the building's roof. While the contractor is responsible for inspecting and maintaining their platform and hoists, the building is responsible for providing suitable points to suspend the platform, as well as sufficient anchorage points to secure the lifelines and tiebacks required. Cabin systems are one way to support platforms regardless of whether they are powered or non-powered, contractor provided, or building provided. The components shown here include davit arms, which are indicated by the pink arrows, Davit arms extend up and out over the building edge to provide a suspension point for the platform. The arms mate with davit bases, which is indicated by the yellow arrows in the photograph, and those bases are connected to the roof framing and resolve the forces from the platform into the building structure. The platform itself is indicated by the red arrow, and it's raised and lowered by hoists located at each end, indicated by the green arrows. The hoists have a tooth or grabbing mechanism that grabs the cable and allows the stage to be, or platform to be raised and lowered. Davit systems are often proprietary. There are many different kinds of davit bases. The ones on the previous slide were affixed to the roof framing. This one, in this photograph, is attached to a concrete roof parapet. Davit systems are typically constructed of galvanized steel components. However, arms more often are made of high-strength aluminum alloys to facilitate ease of installation. If you can think about it, the davit arm has to be placed by a worker onto the davit base. So the lighter that davit arm can be made, the better, because it facilitates safe installation of the system. This photo shows a permanently dedicated movable outrigger, which functions similarly to a davit system. Now, where a davit resolves forces into a single point, an outrigger resolves forces into 2 points. In this case, the inner and outer rail on this track, again, which is permanently dedicated to the building. Requirements for building provided outriggers like the one shown here differ from those for contractor provided outriggers, which are significantly more common. This webinar focuses on requirements for permanently dedicated outriggers, not those provided by contractors to access the building on a temporary basis. Non-powered equipment such as rope descent systems or bosun's chairs are also fairly commonplace in the United States. In this case, the platform, so to speak, is merely a seat board upon which the worker rests. Rope descent systems require 2 lines, a descent or working line to support the platform, and an independent vertical lifeline that will arrest and suspend a worker in the event that they fall off their platform. Rooftop anchorages are required to support independent lifelines for fall arrest equipment and to support equipment tiebacks for certain types of contractor-provided equipment. Perhaps most common are individual standalone anchorages shown in this photo, which commonly consist of a ring for securing the line, a post which extends down below the roof level to a base plate that is in turn secured to the roof framing. Now, spacings for these types of anchorages can vary, but typically range from 5 to 10 feet, such that there are a sufficient number of anchorages easily accessible to workers depending on the wide range of drop locations and rigging configurations that might be used on a particular building. Here's a close-up view of a typical anchorage. Note that the most important connection details of the anchorage are concealed below the roof level, and inspecting these portions requires removal of the roofing. There's really limited information you can see about how an anchorage is connected to the structure that's visible above the roof. In this case, to see that, you would actually have to remove a significant amount of roofing around the anchorage. Horizontal lifelines. These are sometimes encountered and can be used to connect lifelines, but not working lines. They're complicated systems owing to the fact that the tension generated in the cable can be many times greater than the applied force. Just like the tension in a clothesline, for example, will far exceed the weight of the clothes it supports. And for those of us who found out that lesson the hard way, playing on our grandparents' clothesline, that's a lesson that we can remember. The forces that get generated in these types of systems are very large. Accordingly, a lot of them have energy dissipating devices that limit the forces that the lifeline system itself will transmit to the roof structure. Permanently dedicated horizontal lifeline systems require engineering, and they can often be misdesigned. For example, in this photo, load from a lifeline attached at the location of the arrow in the photograph would have to travel around 2 90-degree turns to reach the energy dissipating device at the upper right corner of the photo. Due to friction at these turns, the energy dissipating device may be significantly less effective than expected. Well, that's a brief overview of some of the more common types of equipment that you might find on a high-rise roof, just to get everybody thinking about common types of the equipment. So with that, at this point, I'll turn it over to Gwen, who will talk a little bit about design regulations that apply to this type of equipment.
Thanks, John. Okay, I'm going to talk about initially OSHA. OSHA is the Occupational Safety and Health Administration. We all run into OSHA on our jobs. OSHA does not make finding the governing requirements very easy. They are on their website, but they're scattered throughout a number of different sections. It turns into number and alphabet soup, 1910.28 and 1910.66 for building maintenance, and 1926 subpart L for construction. You may also have, and you do have, state and local codes. Local regulations supplement the federal requirements. They can't supersede the requirements. OSHA regulations still apply. And the building codes and reference standards within the building codes also apply. So you have a number of documents and ordinances and legal requirements that need to be complied with. There are even other standards. They're typically voluntary. They're national reference standards, the A120, the A10.8. Again, it sounds like alphabet soup. The I-14. These standards do not supersede OSHA requirements or the building code requirements. They're voluntary unless they're specifically adopted by the jurisdiction. That would be like the local building department. I will note that the IWCA had their ANSI accreditation suspended for a while, and their standard has been administratively withdrawn. So it's no longer an ANSI standard. IWCA's accreditation with ANSI is being appealed again by at least 2 different parties. So I'm not sure whether they're going to have a standard in the future either. There's a new standard published by AEI in 2015. Its purpose is to consolidate and summarize relevant structural provisions in the OSHA regulations into a single document and to present the provisions in a manner consistent with common engineering practice. One of OSHA's problems is that they use a lot of terms that engineers don't really know. They don't have commonly understood definitions, and so there can be a lot of argument about what OSHA is actually requiring. This document puts it into engineering language. It's intended for structural engineers, architects, and building officials. It contains structural provisions, but no electrical or mechanical provisions. And the committee members were structural engineers. The IBC, the International Building Code, you probably all know about this. This 2015 adopts 2 other standards, ACI 318, which is concrete, and AISC, the American Institute of Steel Construction, 360. It deals with steel. These are basically the standards one uses to design concrete and steel elements in buildings. And they're legally required to be used where the IBC has been adopted. They both contain testing provisions that must be followed according to law where the IBC has been adopted. Let's talk a little bit about basic design requirements. Now, John showed you this picture. It shows the hoists. The hoists are the motors. They lift, they raise and lower the work platform or the swing stage that the workers are on. The rated load of the hoist is a number. It could usually be anywhere from 750 pounds to 1,000, maybe up to 1,500, somewhere in there. That is the load that the hoist or the motor can safely and effectively lift. It can lift it, can lower it. It's not actually the maximum load that the hoist can lift, though. The maximum load would occur if you hit a stall condition. If you're coming up the side of the building and you hit a snag, you hit something that's sticking out, the hoists don't know. The motors just keep going and going and going, and those davits that reach out over the side of the building can act like giant fishing poles, basically. They start bending down, and the motor keeps going until the motor stalls out. Of According to OSHA, that stall load can be 3 times the rated load. So when you ask about, well, what's a realistic load, OSHA actually considers the stall load to be a realistic load. So even though your rated load is 1,000 pounds, the motor can actually probably generate up to 3,000 pounds, and that is a load that your equipment may see if something goes wrong. Okay, so we know the rated load. It's usually stamped on the hoist. It may also be stamped on the davit arms. At a minimum, davits and permanent outriggers must be able to support 4 times the rated load of the hoist that they support. And again, that's because these are motors, and the motors may keep going even in maybe when they shouldn't. And I talked about OSHA uses unconventional design terms such as rated load, intended load. These terms tend to cause confusion in the design industry and may be interpreted differently by different designers. We will point out that there are no requirements that the equipment remain undamaged in these loads. Many designers design their equipment to remain elastic under these loads so you wouldn't get damaged, but many designers also design these things so that they're at the very edge of what is required. Okay, so for a typical davit, you would design it for 4 times the rated load. However, if you're using a davit for construction, and construction may be as simple as hanging a holiday lights or hanging a sign or painting, OSHA has a different definition of construction than probably most lay people in that respect. If it's used for construction, or if you have a rooftop carriage, the davits would need to be able to support 1.5 times the stall load. Since the stall load can be 3 times the rated load, 1.5 times 3 is 4.5. And that's about 12% higher than a maintenance-only davit. So you have to be cognizant of that when these things are being tested or designed. John showed you a picture of the Washington Monument, and in there was a working line and a fall arrest line for each worker. Each worker needs 2 lines. If something goes wrong with your working line, which is the line you're suspended with, you need a backup line, something that catches you as you fall. The requirement on the working line is 4 times the supported weight. And OSHA defines the weight as 310 pounds for the worker plus his or her equipment. So if you take 4 times that, that's 1,240 pounds. For obvious reasons, the fall arrest anchorage needs to be independent from the working line anchorage. The fall arrest line anchorage needs to be designed for 5,000 pounds. Now there is an out in OSHA that says if you have a complete fall arrest system and it maintains a factor of safety of at least 2, and it's used under the supervision of a qualified person, you don't necessarily have to use 5,000 pounds. The problem with that that we see is the requirement that it has to be used under the supervision of a qualified person. A qualified person per OSHA is someone with a recognized degree or professional certificate and extensive knowledge and experience in the subject field. Capable of design. It's basically someone who has a PE. So yes, you can get around the 5,000 pounds and potentially design for something less. However, you're going to need someone with the equivalent of a professional engineering license in order to do that. And that becomes cost prohibitive. So generally, fall arrest line anchorages are designed for the 5,000 pounds. In addition, on the right, you can see the working line anchorages. Since workers sometimes connect to the wrong thing, they'll connect their working line to a fall arrest anchorage and vice versa. It's generally good to design all anchorages on the roof for the 5,000 pounds that you're trying to support. If you're interested where the 5,000 pound number comes from, that's a historical number. It sounds like a lot, given that people may only weigh a few hundred pounds. But remember that this fall arrest line is stopping someone who's falling. And the way the lanyards work, you can easily fall 6 feet if your working line gives out. According to OSHA, if you drop test the 300 pounds, 6 feet, you can you're allowed to generate about 2,500 pounds of force. And so if you have a factor of safety on that, which 2 is a fairly common factor of safety, you get the 5,000 pound typical design load. I'm going to turn the presentation over to Rich, who's going to talk about building owner responsibilities.
Okay, thanks, Gwen. Hopefully everybody can hear me. Hi, everybody, and thanks again for attending. My name is Rich Dethlefs, and I'm a structural engineer in the Seattle office of Wisconsin. Although I've been practicing for 20 years, I've spent the last 10 years or so being heavily involved in the facade access industry, including designing, testing, and certifying facade access systems and anchorages. When I first got involved in this industry, I found the OSHA requirements to be extremely confusing, and deciphering those requirements has been a process. In this section, I'm going to discuss the responsibilities of building owners to provide assurances to the users of the building's facade access system. So be prepared. This is going to be the exciting part. Building owner assurance requirements in OSHA are contained in Standard 1910-66, paragraph C. There are 4 requirements, which I will discuss briefly before moving on to the testing and inspection requirements for facade access systems. 1910-66C1 requires that building owners of new installations, which OSHA defines as those installations that were completed after July 23, 1990, or that have had major modifications performed since July 23, 1990, must provide the users of the system in writing before each use an assurance that all of the support elements of the system meet the capacity requirements of OSHA 1910-66. So how do you do that, you say? Well, in 1910-66 C2, OSHA further clarifies the basis of the owner's assurance. It states that the assurance must be based on the results of field tests of the installation before being placed into service and following any major alteration. So ideally, the contractor would load test all of the structural components of the facade access system under the direction of a professional engineer prior to turning the system over to the building owner. In this case, the professional engineer overseeing the testing would provide a certification of the system to the building owner, or you could receive that certification from the contractor, which would allow the owner to provide the required written assurances to the user. Unfortunately, what we frequently find is that the systems are not adequately load tested in the field prior to being placed into service, or they're not load tested at all. And what building owners often receive is just a set of design drawings stamped by the designer of the facade access system. 1910-66 C3 requires that building owners of all installations, both new and existing, so those that were built prior to July 23, 1990, provide written assurance to the users that the installation has been inspected, tested, and maintained in compliance with the testing and maintenance requirements of 1910-66. Now, it's difficult to discern exactly how this requirement is different than the requirement of 1910-66 C1. The difference is that this requirement only requires that you provide assurance that the system has been inspected, tested, and maintained in compliance. However, if you go to the section on testing, the first testing requirement contained in paragraph G requires that all the elements of the installation be tested prior to being placed in service.
So again, it would appear that both new and existing systems need to be tested in the field in order for the building owner to provide the required assurances. That's one of those areas where OSHA is a little bit unclear. Lastly, 1910-66 C2 requires that the building owner provide assurances to the users that all fall protection anchorages meet the capacity requirements of OSHA 1910-66 Appendix C. So regardless of how you interpret the assurance requirements for existing systems, be it davits or roof carriages, the owner is clearly required to provide written assurance to the users that the fall arrest anchorages meet the minimum capacity requirements of OSHA, which were discussed previously by Gwen. Finally, the last assurance requirement is contained in 1910-66 C4. It states that the employer is the company that will be using the equipment, so maybe the window washing company. The employer will not allow their employees to use the system until receiving the required assurances from the building owner. So if you're an owner or manager of a property and you never had your facade access system tested and certified, and you cannot provide the required assurances to the users, you're at risk of the users refusing to use your equipment. And in fact, they are in violation of OSHA if they do use your system. Okay, next I'm going to spend a little bit of time talking about the testing and inspection requirements in OSHA. The testing requirements in OSHA are contained in 1910-66 paragraph G. This paragraph requires that all completed facade access installations must be tested in the field prior to being placed into initial service. The in the field portion of the requirement is important because even though an equipment supplier may be able to certify the capacity of their equipment, they cannot verify that the equipment was properly attached to the building. The load testing allows the professional engineer in charge of the testing to provide the required certification of the installation to the building owner. This is why it is so important that designers of facade access equipment provide equipment that is strong enough or stout enough that it can be load tested in the field to the full required design loads. There are no requirements in OSHA to perform load tests again later in the life of the installation, unless a major alteration to an existing installation is performed. However, if an owner chooses to do so, or if there is some question about the capacity of the installation, such as significant corrosion or impact damage, or if no evidence exists that the initial testing was ever performed, then it may be prudent to re-verify the installation capacity through load testing. Lastly, yearly inspections of facade access installations are required to be completed by a competent person. A competent person is defined by OSHA to be a person who, because of training and experience, is capable of identifying hazards or dangerous conditions in powered platform installations, and of training employees to identify such conditions. Okay, before I turn this back over to Gwen, I'm going to spend a little time demonstrating how we perform load tests on common types of facade access equipment. But before I do that, how about some sage advice from the most interesting man in the world? That looks like some good sage advice to me. It's important to remember that anchorages and equipment attached to a building are not factory fabricated widgets. Although the anchorages or davit bases may all look alike, the attachment of the various anchorages to the building may vary considerably. One anchorage may have been installed perfectly, while the anchorage installed 10 feet away may have mistakenly had the base plate omitted. So although the first anchorage may easily sustain the 5,000-pound design load, the anchorage 10 feet away may fail at 500 pounds. That is why it is so important to test every single component of a facade access installation. This is a picture of an aluminum davit arm, indicated by the yellow arrow, sitting in a davit base, which is indicated by the red arrow. The davit base provides the attachment of the davit arm to the building, and the field testing is required to verify the capacity of the davit base and its attachment to the building. Now, if we also question the capacity of the davit arm for whatever reason, possibly we can't find the manufacturer's documentation on the davit arms, or we aren't sure what alloy the aluminum is, we can test that too. But we typically would not perform this test by dropping weights over the side of the building. This photo demonstrates how we would typically test a davit arm on the building roof using a come-along with a load cell, or possibly a hydraulic jack. This photo indicates how we would typically load test davit bases, using a hydraulic jack, a test arm, and wood cribbing to redistribute the load to the roof. We test the connection of the davit base to the roof structure. The test arm can be moved from location to location on the roof to quickly and efficiently load test a number of davit bases in a single day. Prior to performing the test, we would verify through analysis that the testing would not cause damage to the roof structure. This photo shows a number of roof-mounted anchorages that would typically be used to support working lines or fall arrest lines for rope descent type access, or would possibly provide tiebacks for contractor-supplied outriggers. We commonly refer to these as pedestal type anchorages, and they are typically either anchored to a concrete roof deck or welded to steel roof beams. It's important to note that the anchorages must be tested in the direction that they are intended to be used, which is typically toward the roof edge. Simply pull testing the anchorages against one another does not demonstrate adequate capacity of the anchorages in the direction of use. If someone ever tells you that it doesn't matter what direction the anchorages are tested in, then you may want to rethink who you are getting advice from. In many cases, there is simply nothing in the direction of the roof edge to pull against to test an anchorage. That is why we've developed the test arm shown in the photo above. This test arm can be fitted over the top of a pedestal anchorage and can test it in any direction. Using this test arm with a hand-operated hydraulic ram and some cribbing, we can test a large number of anchorages in any direction in a short period of time. This is a photo taken of a load test that does not adequately demonstrate the capacity of the anchorages in the direction of use. Sure, it's simpler and easier to test two anchorages against one another. In this way, you accomplish two tests at one time, and you have another anchorage nearby to react off of. However, the test does not demonstrate the required capacity of the anchorage in the direction of use. For this reason, we would not consider this to be a valid load test. This photo demonstrates the application of a simple pull test. In this case, the anchorage was a threaded eye bolt that was attached to a threaded insert. The eye bolts supported working lines and fall arrest lines going over the roof edge and were loaded in tension to 5,000 pounds. All of the eye bolts and inserts were tested and were shown to have adequate capacity. Sometimes we come across unique challenges. This photo is one of the unique systems we've tested. It's an older roof carriage supported by rails. The carriage supports a powered platform that services a high-rise building. We performed an analysis considering 4.5 times the rated load of the hoist to satisfy the requirements to support construction activities with the powered platform. Since the hoist loads would be partially offset by the weight of the carriage itself, we used hydraulic rams and load cells to determine the weight of the carriage at the back rail. The test load on the back rail was then the difference between the uplift caused by the hoist loads and the weight of the carriage. With that information in hand, we then tested all of the back rail connections to the building using a test beam and a hydraulic ram. The testing demonstrated that all of the back rail connections were adequate to resist overturning of the carriage due to the full design load of the hoist, which in this case, again, was 4.5 times the rated load of the hoist. This photo is of a different building where we were also testing carriage rail connections. I threw this photo into the presentation just to make a quick point. The arrow in the photo indicates a joint in the rail beam. The typical connection had 4 bolts at the rail connections. However, it was observed that where a joint occurred, there were only 2 bolts on either side of the joint. So at these locations, we performed the uplift test on both sides of the joint to ensure that the connection would work, no matter which side of the joint the carriage was on. These 2 photos show us testing the end anchorages of a horizontal lifeline system. As John stated earlier, similar to a clothesline or even a piano wire, if you pull sideways on a taut horizontal cable, the forces in the cable will be amplified, possibly doubled. The forces in the line are then transferred to the end anchorages. This is important and is often misunderstood. The end anchorages of a horizontal lifeline system are often subjected to loads far in excess of the 5,000-pound fall arrest loads that they are intended to resist. For horizontal lifelines that pass through many anchorages, the analysis can be quite complicated. In any case, this analysis should be performed prior to load testing so that the appropriate test loads are used in the testing. Lastly, this photo shows an overhead track and trolley system. The inset photo shows that there are 2 trolleys in the track, one to support the working line and one to support the fall arrest line of the user. One of the primary requirements of OSHA is that the fall arrest anchorage must be independent of the working line anchorage. We do not consider 2 trolleys sitting side by side, supported by the same track, to be independent. Any failure of the track or its connections would cause the worker to fall with no workable lifeline. In addition, we found these systems are virtually impossible to load test after the building is completed. If this system were to be tested, it would have had to have been performed during construction when the track and connections could be tested without putting the tester at risk. Well, that's it for me. Hopefully I've helped explain the assurance requirements for owners and the testing and inspections that need to be performed in order to provide the necessary assurances. With that, I'll turn it back over to Gwen to talk about some of the poorer industry practices that we've come across in our experiences with this particular industry.
Okay, thanks, Rich. Okay, so I'm going to show some of the problems that are endemic in the facade access testing industry. We've seen a bunch of issues, and I'm going to talk engineering to you, but like this photo shows, I think you're not going to need to be an engineer to figure out what's wrong, just as you don't need to be a boat owner to figure out this is not how you put a boat in the water. The first topic I'd like to cover is half-load testing. There are 2 standards, the A120 and the administratively withdrawn I-14 standard. Both of these standards limit testing facade access equipment to 50% of the full design load, the factored, what engineers call the factored load, or the required strength or the required capacity. The 2 organizations that are listed there provide reasons for not wanting to test to the full amount. Their reasons include they don't want to damage the roofing, and they don't want to damage the equipment that's being tested. At WJE, we believe that the lives of the workers are more important than worrying about damaging the roofing. If you're doing a load test, there is some potential to damage the roof, and whether you go to half of the load or all of the load, you could still damage the roof if you don't do it right, or if the roof is extraordinarily soft. So you have to take precautions not to damage the roof, and to look when you're all done to make sure you haven't damaged the roofing. And we would rather have the equipment fail during a load test than when someone's hanging off the side of the building using it. So we think the primary reasons given to avoid testing to the full amount are really not very good reasons. I will say that the National Council of Structural Engineers Associations, the American Institute of Steel Construction, a bunch of professors, including professors at Stanford and University of California at Berkeley, and numerous other well-known structural engineering companies all concur that if you're going to do load testing, you need to do it to the full amount. I'm going to try to explain why in non-engineering terms. This is an example of how load testing can be misused. This is a project we worked on. We were called in after the fact. There were 24 anchors on the roof of this building that were load tested to half of the minimum required strength. 20 of them held the load. 4 did not. So 4 couldn't even hold half of the load. The engineer in charge certified that the anchors are, the 20 that passed are acceptable and will hold the full amount. So let me give you an analogy. Suppose your employer says, hey, we need a fleet of 24 automobiles to go around, look at properties or whatever. And you're going to want cars that can go at least 70 miles per hour on the highway. So you go to a car salesman, and the car salesman says, well, you want them to go 70 miles per hour. That's a requirement that you have. But I only want to let you test them to 35 miles per hour. I think you can extrapolate. If it goes 35, it must be able to go 70, right? So personally, I would tell the salesman, no, I need to take it out on the highway. I want to make sure that they work. Now, suppose that you go ahead and you believe the salesman. You say, okay, all right, I'll agree to a 35 mile per hour street test of these cars I'm going to buy. And of those 24 cars, 4 of them can't even go 35 miles per hour. I can tell you that at that point, I would seek out probably a new manufacturer of cars. I wouldn't use that make or model. I wouldn't buy that make or model. And I think most people would say, if you can't even make 24 cars that all can go 35, we're not buying that. Unfortunately, in this case, the engineer actually did certify that the 20 anchors that held the 2,500 pounds, he certified that they can resist the full 5,000 pounds that they're required to resist. On this building, we said we were actually going to use these anchors. We, at WJE, do facade inspections and facade work. We looked at the report and we said, we're not getting on this building. The load tests don't show what they need to show. Furthermore, you had 4 failures at less than half of the full load. In addition, it turned out that these anchors were tested in the wrong direction. They were reacted against each other, not towards the edge of the building where a fall arrest load would be pulling. So we felt that the tests were so deficient, we advised the owner to find new anchorages or install new anchorages. Here's another case study. This is load testing of davit bases. These davit bases were previously tested to 2 times the rated load. So again, it's half. They all passed. And they were certified as being capable of resisting the full 4 times the rated load. At some point, the owner said, you know, we really should test these again to make sure that everything's okay. When we tested them to 4 times the rated load, we found a number of davit bases that fractured during the load test, and the load test did not achieve, of those davits, the load test did not achieve the minimum required strength that they were required to have. So again, the davit bases, some of them were deficient, and the half-load testing to 50% of the full load, or 2 times the rated load, did not catch the problem. Furthermore, if we had only tested some of those davit bases, most of them actually passed the test, the full load, and most of them passed fine. It was a few that didn't. If we said, you know, we're going to select 20% or 10%, some arbitrary number of davit bases to test, there's a pretty good chance we would have tested those 10 or 20% davit bases and everything would have been fine. And if we had certified the davit bases based on that partial inventory testing, we would have been certifying that the ones we didn't test, and some of them had problems, we would have certified that they actually met all the requirements, and that would be wrong. Here's one more simple example. Again, it's a davit base that's being tested. You can see the anchor bolts down at the base of the davit base. This was a new retrofit installation to an existing building. The building didn't have any facade access equipment, so we were retained to design new davit bases. We required that all the davit bases be tested prior to be put into use, and at least one of the davit bases failed, didn't achieve the 4 times the rated load. When we looked at what happened, we actually found that the anchor bolts, which were supposed to be epoxy anchored into the slab a certain amount, some of them weren't. Some of them, they must have hit reinforcing steel in the slab, and rather than move the hole or move the davit, the contractor just put it in short. It wasn't caught during inspections. It was built, and the only thing that caught it was a load test to the full amount. Now this isn't a davit. Just like the boat example in the very beginning, I think this sort of drives it home. Suppose you're out hiking with 2 of your friends. You come to 2 rickety old bridges. You can choose the one on the left or the one on the right. Your hiker friends are braver. One of them weighs 200 pounds. That hiker will take the bridge on the left, and the hiker that weighs 100 pounds will take the bridge on the right. And for the sake of argument, we'll assume that you weigh 180 pounds. Both hikers cross the bridges. So the bridge on the left has now been tested with 200 pounds, and the bridge on the right has been tested with 100 pounds. I don't know about you, but I would definitely, if I weigh 180 pounds, I'm taking the left bridge. That one's successfully been tested with 200 pounds. It didn't break. The one on the right, it's been tested with 100 pounds, so we know it will take a 100-pound load. We don't know it will take a 180-pound load. Okay, for a brief summary. So davits and outriggers. They need to be designed for 4 times the rated load of the hoist. That's non-negotiable. If they're used in construction, or if it's a rooftop carriage, they need to be designed for 1.5 times the stall load of the hoist. Stall loads can be up to 3 times the rated load. 1.5 times 3 gives you the 4.5 times the rated load. Fall arrest anchors, again, must be independent. You need to have a completely separate backup system so that if something happens to your primary support, you're still supported. These need to be designed for 5,000 pounds per worker, or there is an out. You can do use a 2 times factor of safety, but you have to use it under the direct supervision of a qualified person. That's essentially a professional engineer. That becomes cost prohibitive. We typically recommend to our clients that they just use the 5,000 pounds per worker as the minimum required load and not to skimp on the design. In terms of testing and certification, testing of the anchorages in the field is required. Davits, bases, all this stuff needs to be tested before it's used. and they need to be certified, and you get the certification from a professional engineer. Owners are responsible to provide assurances to the people working on their equipment that everything meets OSHA's requirements. Employers, that's the window washers, they're not allowed to let their employees use the equipment without receiving the assurances from the building owner first. And I've talked about the poor industry practices. The three most common are testing to only half of the minimum required capacity, testing in the wrong orientation. That's often easy, but it often gives you the wrong answer because you're not testing it in the direction that the anchorage will be used. And testing only some of the equipment. Again, this seems easy. We're only going to test some of the equipment, but you really want to test all of it for the reasons we've discussed. John, do you want to moderate questions? It looks like we have a few minutes.
Yeah, thanks, Gwen. So just as a reminder, if you have questions that you would like to ask, we have a few already that have come in. Look for the dialog box in the upper right corner of your screen. Click on the questions box, type your question in there, and we will try to get to as many as we can. First question, Gwen and Rich, I'll throw out. If an anchorage is deformed during a load test, do we need to have it replaced?
This is Rich. I'll take that. In general, you should at least take it out of service until it's been evaluated by a professional engineer. It may be possible that the deformation doesn't affect the capacity at all. So I would say have it evaluated, possibly reload tested, and chances are it may be able to be reused.
And this is John, I would add to that, most likely all anchorages will undergo some sort of deformation, right? I mean, usually it's very minor if they're properly designed. If it's more than a little bit, you might consider some uneasiness that workers might have in looking at an anchorage, even though it may be able to take the load. They may look at it and say, well, this doesn't look as good as the one next to it, so it must be deficient, which may or may not be the case.
Yeah, John, I would add that there are some anchorages that just do not lend themselves to load testing at all. There are what I would call single-use anchorages for fall arrest lines that when they get loaded, they just bend all the way over. It's a very ductile failure. They just bend, and then they can take very large loads. But obviously, if you do a load test and you load test it such that it bends all the way over, you're going to have problems with getting anyone to use it because it probably shouldn't be used at that point. So it depends on, I would say it depends on the deformations that we're talking about. If everything deforms, everything moves when you put load on it, if it's noticeable or if it reduces the capacity of the anchorage, then that needs to be addressed.
Okay, another one. How often do I need to test my davits and my anchorages or have them certified, and what's the difference between testing and certification?
Oh, this is Rich. I'll take that. Testing is a means to get the certification. A certification is nothing but a statement from a qualified professional stating that to the best of their knowledge the equipment has the capacity required. So that's the certification. Testing is a means to get the information to provide that certification. As we discussed, the systems really only need to be tested once. If they're ever modified or damaged or there is some question about their capacity that maybe it has been reduced, then you may want to, it may be prudent to retest them or have them reevaluated. but certainly according to OSHA, that it's only required that they be tested prior to being initially placed into service.
Rich, I would add that there may be some anchorages or davit bases where portions of the system disappear below the roofing membrane. And waterproofing of those penetrations can be difficult. So there's some potential for water to get in there. You could have some long-term corrosion going on that you can't really see because it's below the upper level of your roofing. So at some point, let's say you have substantial roof leaks, your roof is very old and you haven't addressed it yet, there's potential there for hidden corrosion to be going on in the anchor bolts or the welds or the metal that's underneath that roofing. So in cases like that, that would be another case where you might want to do some load testing to make sure that everything still is working the way it's intended.
Agreed.
We have a question here, or a couple of questions that are kind of related. I'll paraphrase. What constitutes an inspection in the required 12-month period? So talking about OSHA required inspections, what kind of things are involved in one of the annual inspections? A couple of questions on that topic.
I would say the inspections usually are just visual. There's certainly no load test required every 12 months. That usually someone goes out, they're a qualified person, right?
Competent.
They're competent. They're competent person. Sorry, they're two words that OSHA uses that I have to always go look them up. So a competent person can go do that. They don't have to be a PE. They don't have to do load testing. It's usually visual.
And the purpose of that is to identify if there's anything going on that might require some further verification of the capacity like we were just discussing.
Another question came in is what related to an OPOS, and for those of you who are not familiar, that's it's an operating procedures outline sheet that generally kind of gives an overview of facade access techniques and equipment. And a specific question here is an OPUS required for OSHA compliance?
The OPUS is actually, I believe, a California term. We sometimes call them roof access plans. Rich, can you speak to OSHA's requirements? In California, you would need an OPUS if there's anything unusual about your roof access plan. It tells the workers how to use all the equipment on your roof, basically.
Yeah, the OPUS is a requirement for Cal OSHA. I'm not aware of federal OSHA requiring an OPUS. In Washington State, there are requirements for a use plan. It's I can't remember the exact term, but it's defined a little bit differently than an OPUS, and the requirements are a little bit different.
And this is John. I would add, I'm not aware that there's a specific requirement in OSHA that uses that phraseology that you have to have an OPUS, but it's generally good practice. And I think that what OSHA prescribes is that the contractor has is required to kind of come up with an emergency plan with a plan of access. The building is supposed to supplement that, so there's kind of some shared responsibility there, but it's maybe not as direct as you might find in Cal OSHA, for example. Another question is, what kind of scenarios exist where an accident could generate 5,000 pounds of load on an anchorage?
Well, this is Gwen. As I discussed, 5,000 pounds is a very large number. If you have a worker who has a lanyard that's not shock absorbing, that harness system is allowed by OSHA to generate around, I think it's 2,540 pounds if the worker falls 6 feet. problem is people misuse their equipment all the time. They may have the lanyard attached to the fall arrest line very low, so they have to fall a distance before they pass the lanyard, and then the lanyard can be up to 6 feet long. So you can have a longer fall distance. You can have a heavier worker than the OSHA requirements. Both of those could generate loads that are greater than 2,500 pounds, particularly if there's not a shock-absorbing lanyard attached. And again, you know, engineers want to design for a load, but they also want what's called a factor of safety. So we take the OSHA load and the OSHA maximum load that's allowed to be developed and multiply it by 2, and then we get 5,000 pounds. That's sort of a backwards derivation of that number.
Yeah, certainly the last thing you would want to do is design your anchors to just resist the load that you anticipate may occur. So if 2,500 pounds is the load that OSHA allows to occur, you don't want half your anchors resisting that load and half not, because that's like the average capacity of your anchors. You want to have a significant safety factor in excess of that so that you ensure there's no way that that load could ever fail that anchor, whether there's a defect in the anchor or whether there's additional load applied in excess of the required load. You've got to make sure you have a safety factor. So that's why OSHA requires the minimum capacity of 5,000 pounds.
Okay, it's a little bit after 2. There's still a couple of questions that we weren't able to get to. I apologize for that. We will follow up with folks individually for any questions that we weren't able to address. And if you do have questions that you would like to follow up with WJE about, feel free to contact either myself, Jon Lewis, or Gwen, or Rich. Our email addresses are on the screen there. We hope to provide a copy of this presentation to everyone shortly. And with that, we'll say thank you very much for joining us and have a great afternoon.
Thank you
very much.